in vitro to in vivo amyloidogenesis. What is lost in translation? So, Professor Velotti, please.
I'd like to thank deeply for the invitation. I'm really honored to be here today in this great environment, scientific and cultural environment. The title of my presentation will include the word translation. Because actually I think translation is a crucial part of modern medicine and particularly important in the investigation on amyloid diseases. Translation is sometimes a difficult task, and in order to have a faithful translation, we should know very well the meaning of every word and the meaning of the entire document. And I present the Rosetta Stones and one of the enterprise of the Western country that took more than 50 years to translate from the ancient Egyptian language to the Greek, through an amazing effort by French and Japanese, and sorry, this is Freudian lapsus, French and British. Translation is certainly a part of our path in medicine now, and is mostly aimed to identify diagnostic and therapeutic tools from the precise knowledge of the disease, the natural history, the molecular basis of the disease. And of course, all the progress we made in precision medicine can directly go into the translation medicine, where we start for a simple model in the test tube, moving to more complicated model in C. elegans, Drosophila, mammalians, and the idea is that this is a path in which we start from the very well-known property of the disease, and we go back to the patients with better therapy and better diagnostic tools. However, I think the path is not only in one way, but probably also from the models and the response to therapy, we know more about models first and about the natural history of the disease. And this part is particularly important, and I will present today some experience mostly made in this area of the path, from the molecular diagnostic to the first experience in making a molecular model in the test tube. And this part of the model is very important, as I said, and probably if we don't make good model of the disease, it will be difficult to understand the disease itself. And this is the sentence of Richard Feynman, the Nobel Prize in 1965, shared with Professor Tomonaga from Japan. And he said, what I cannot create, I don't understand. And I think it's particularly important and true for amyloid disease. This is a path of the progress in amyloid diseases, from the early observation of the histological deposition of amyloid until now, where this is from a nice review from Buxbaum and Linke in 2012, and I added just a few days ago the last discovery of the effect of the expression of RNA expression that are now successfully used in clinical trial and approved as a drug for treating patients. And the discovery of this new treatment is mostly based on some discovery, basic discovery on the effect of RNA interference in the inhibition. So there is a strict conjunction between improvement of technology and basic knowledge and progress in understanding and treating the disease. But the question is, are we sure that this is a straight path? Or most likely is a tortuous path in which we make mistake, we go back, we found again, and probably this is a strong invitation, mostly to young investigators, to keep critical thinking and look at the inconsistency, at the strange results, and the interaction between the inconsistency between hypotheses and experimental evidences, and insist and looking for the truth. Backing to our subject on amyloid, I think the path we know now is from plasma protein or proteins that normally have a beautiful function in the body to the deposition in the tissue. We can start from the protein to the tissue deposition or back, as mostly the physicians do, starting from the observation in the clinic and going back. And this is the path required from the globular protein, mostly for systemic amyloidosis, a partial unfolding of the protein, first aggregation into prefibrillar state, then into fibrils, and deposition in the extracellular matrix of target organ. One of the crucial part, and this is part in which precision medicine and translational medicine will be linked, is the partial unfolding of the protein due to mutation, intrinsically tendency to lose the structure like in beta 2M or post-translational modification. But one crucial point is where is coming the energy that in vivo in the body can induce stable protein nitrostyrene to lose the quaternary structure, the tertiary structure, and go into a state that is favored in the aggregation. And particularly my interest is searching for the reason why in vivo protein from the native state can jump to a condition, thermodynamic condition, in which we lose some of the structure and start this pathway into the aggregation. This is our major subject now in the laboratory, the investigation of mechanism of transthyretin amyloidogenesis, starting from the theory that is now dated to 1992, primed and discovered by Jeff Kelly and Per Armstrong. The audience contributed a lot to this discovery, in which the transthyretin aggregation required the dissociation of the tetramer into monomer and dimers that start to aggregate into polymeric aggregated state. And what is very interesting and peculiar for transthyretin that generates such a strong work on finding a cure, to finding a therapy, is that he has a natural ligands with high affinity in one of his pockets, associated to a second pocket in which we have lower affinity due to negative cooperativity of the binding of the two small molecules. Thyroid hormones are the natural ligands, and then on the basis of thyroxine structure, many compounds, and one in particular that is approved for treatment for amyloidosis now, was used to prevent the aggregation, because if you stabilize the tetrameric structure, you prevent the dissociation at low pH, pH 4.5 at least for the wild type protein, that is also one of the amyloidogenic protein in senile people. You can prevent the dissociation. But in parallel to this model in vitro, in the test tube, we look back to what was found in terms of structure and sequence and primary structure of TTR fibrils in natural deposits. And this is some pioneeristic work done in Sweden by Erik Lundgren at the beginning in 1993, discovered that in transthyretin natural fibrils you can find a fragment starting from position 49 due a cleavage between a lysine 48 and threonine 49. And this was, for many years, was eaten, and then later in 2005 and now in the recent year, the presence of this fragment became more interesting for researchers, and the Westermark group has divided the type of fibrils in type A containing this fragment 49127. This is a major fragment, at least in its laboratory, and type A, in which you have very small amount or nothing in terms of fragment. But most of the fibers contain the fragment, and I think now all in the art you always have, independently of the type of mutation, you have the fragment 49157 plus other minor fragments. The presence of fragment is generally associated to a poor prognosis in terms of cardiac outcome of any therapy. So when we look at one case, a very aggressive form of disease in which we had the mutation of proline, from proline in position 52 to, from serine in position 52 to proline, we immediately look, because this was a very aggressive form of the disease, one of the most aggressive form of cardiac amyloidosis we have seen in the central UK. We look at the fibers and we found as band 2 a lot of fragment 49127. So we started in looking at the role of fragments just from a pathological observation, the molecular characterization of a pathological specimen. These are the fibers extracted from the heart. So because the cleavage is between a lysine and a threonine, we immediately try to reproduce, translate in a test tube this observation. We put some recombinant tetrameric protein, homotetramer of the mutation, including the wild type and other, to expose to little amount of trypsin, the mother of the serine proteases, and immediately in 3 minutes we saw that even in physiological condition, in PBS, without any agitation of the system, we can generate a fragment. The fragment is the fragment 49127. Then if you live longer, you have a subfragmentation of this fragment and the protein too. But what was quite interesting was the fact that just adding trypsin, the cleavage, you have an aggregation of fragment and monomer, because we discovered that the cleavage in this position dramatically destabilized the tetramer, and the tetramer dissociate in physiological condition. So the classical feature of fibers were imaged by EM, X-ray, AFM, and you see if you wash along the precipitate, you remove everything except the fragment 49137. I think this means that it participate to the stable core of fibers. But the point is, because we have fragments in vivo for many other mutations, and not only for this rare mutation, the question was why the other protein and the other TTR are protected from the cleavage. So we went back to our recent knowledge on the stabilization in physiological condition of amyloidogenic protein, and we thought that probably what we learned from another protein, a rare variant of beta-2M that you can induce to aggregate just exposing to biomechanical forces in physiological condition, probably we require some perturbation of the tertiary quaternary structure of TTR in order to make the TTR susceptible to the cleavage. And then we expose to agitation in the presence of hydrophobic forces to the other variant, and you see here, with the exception of the well-known 119 methionine variant that is a protective mutation in TTR, under turbulent flow and exposure to hydrophobic surfaces, also the other variants that are normally not suitable for cleavage become cleaved, and they aggregate, make Congo red, positive staining, and nice EM fibers in the precipitate. So we studied this, we use the term mechano-enzymatic mechanism of cleavage, because we should associate the proteases to some perturbation due to mechanical forces that are the forces that in vivo probably can provide sufficient energy to perturbate the protein. And this is quite a inspiring sentence by Sir David John Weatherall, who worked on a rare disease, mostly on hemoglobinopathy, And he said, rare disease provide opportunity to study human physiology, and the major scientific perspective often provide insight to more common disorders. This was a study, our study was based on a category of rare disease, but particularly in a very rare form inside the category of rare disease. So we should never stop to look at the very rare and unusual cases nature is offering to our eyes. So now I think in parallel to the mechanism, to the model of dissociation at low pH, now we can have a mechanism in which the aggregation starts from cleavage, dissociation, and monomer fragments go into fibrils. And if you compare the type of fibrils you can get now with this method, it seems to look like more similar to the ex vivo fibrils as before. This cleavage is associated to instability of some part of the protein, in particular the CD, the loop interconnecting the strain C and D. And of course, we thought maybe by a stabilizer we can also inhibit this mechanism, because if stability is associated an element that make the protein more or less susceptible to cleavage, the stabilizer already available in the clinical trial, and some of new stabilizers we are working for a few years in London that has the property to have a bivalent structure, because it can occupy both binding site and occupy the central channel of the molecule. They can inhibit the cleavage, and it's true. You can inhibit by tafamidis, by diflunisal, and also with MDS84, this molecule. And probably we think that the aim of better stabilization, at least to inhibit the cleavage by the proteases, would require the occupancy of both binding site of the molecule, and not only just the first with the high affinity. I would say that the proteolytic cleavage is a very potent mechanism of amyloidogenesis. And if you look at what we call now minimal residual disease, so you have the inhibition of with the drug. But if you spin down at very high speed the material, even at the complete inhibition, apparent inhibition on the thioflavin assay, you still have some part of the molecule, some pelleting of the solution, in which you can still recognize fibrils. This is even done with our molecule that we consider the most potent inhibitor so far in the pre-drug phase, but also we talk upon tafamidis, and we still have a little bit. The meaning, the clinical meaning, I don't know which is, probably this will be degraded by the protection system of the body, but certainly is a potent system for making fibrils in vivo. This method, this model of fibrillogenesis using the trypsin, the cleavage, highly depend on seeds. Without seeds, we have a lag phase that is prolonged if you reduce the concentration until 1 micromolar. But if you add seeds, you make uniform the lag phase become identical, and you have a better yield of fibril formation. And this is, I think, recapitulates some property of the disease in vivo, because I think TTR amyloidosis is highly dependent on seeds also in its natural path. The GAGs strongly activate the aggregation, reduce the lag phase, and increase the yield. This is another thing that makes similar this type of amyloidogenesis to other type of amyloid protein aggregation, and also has some impact on recapitulating the disease in vivo. Of course, I will not escape for the tortuous pathway of looking for a relative truth. And of course, the objection, main objection was, Yes, trypsin is located in the duodenum. It's very difficult to have in other tissue. So we search for the proteases starting from classical biochemical approach of enzyme purification from distant tissue, and what I can say, we never found in any tissue a proteases that can recapitulate what we do in vitro with trypsin. So we move to another way, and we look at what was more similar in terms of structure to trypsin and in terms of specificity to trypsin. And we single out a few proteases, and thanks mostly to Alessandra Corazza in our lab, we select a few proteases, and one of them was plasmin. And look at the effect of these proteases on the mechanism of the disease. And you see some proteases that have the same specificity, apparently you expect the same specificity of trypsin, that are not effective at all on TTR. This is trypsin in blue, and this is plasmin in red. And plasmin cleave at least the proline 52, but also other variant of the same site. We have fragment 49-127 with plasmin or with trypsin, and if you add alpha-2 antiplasmin at different concentration, you abrogate partially or completely the cleavage. And then you can recapitulate in a more physiological-like model what happened. This is a panel in which we add fibrinogen at the beginning and thrombin, because fibrinogen is cleaved by thrombin, making fibrin, activating and activate plasmin. This is turbidity of the system. In red is in the presence of the proline 52. In blue is in the presence of methionine 119. The turbidity starts to grow because you have the formation of the first polymer, fibrin, and then of course plasmin activate and degrade everything, solubilize, and the turbidity reduce if you have the non-pathogenic protein, the methionine 119. But if you have the proline 52 variant, the activation of plasmin also cleave the transthyretin, and then you start to have turbidity. And if you monitor the system with thioflavin, you see blue, the methionine 119 does not form amyloid, but the amyloid is formed by the proline 52 variant, and the effect confirmed. So at the end, we came out with this model, which we hypothesize that plasmin can have a major role. Plasmin is activated from plasminogen in a continuous way in our body. We just physical exercise or normal life activate plasminogen to plasmin in the circular, in the vessel, where microthrombi are normally formed and immediately removed by plasmin. But also there is another way by which plasminogen is activated, mostly on the exercise, as in the extracellular matrix, because in the extracellular matrix, plasmin degrade and remodel collagen, other fibrous protein. So we have two sites in which plasmin can cleave other protein, and of course variant and TTR wild type. So we have the cleavage, and I think for many years, mostly for the wild type, and for less years in the variant, we have a complete degradation through this way of transthyretin. But when you have the first nucleation or the aggregation, you start to make some fibers in the extracellular matrix. This is our model so far for the TTR. But of course, I cannot, and I am pleased to show mostly to the young scientists here, a sentence of Sir Peter Medawar, Nobel Prize in 1960. Most of the business in science testing logical implication of hypotheses. A lot of hypotheses are also on my work so far. But this consequence assuming for the timing that they are true, is what we do normally. The problem is we should keep alive the dialogue between the possible and the actual, the one imaginative and the other critical, between conjecture and computation. I strongly recommend to young scientists to read this book, The Advice to Young Scientists by Peter Megawan. And then I will thank all my collaborators in London and in Paris, because I still commute a lot from University of Pavia in London, and Marpe is our mentor, and all the other people working most in London. Thanks.
Thank you very much, Professor Belotti. So now this presentation is open for other discussion. Any questions or comments?
Yes, I think it was a very interesting presentation. I've also been thinking a lot about blood coagulation being involved in amyloidosis, and many others have too. So the plasmin thing was new to me, but the trypsin is my question. Do you only get this stable fragment? So if I was to express the mutant and trypsinated, would this fragment be purifiable because it aggregates rapidly? Because when I have used trypsin on TTR, I've done it to fully trypsinate. I don't remember the exact conditions I have used, but I get full coverage if I do a trypsination mapping on TTR. And you don't see further cleavage. What is protecting? Do you think aggregation is protecting from cleavage?
Proteolysis in amyloidogenic protein is an old story. You have actually two possibilities, or degradation, complete degradation, making peptides, more peptide, if you don't reach the critical concentration for aggregation. But if you reach the critical concentration for aggregation and you make fibers, then the further degradation is minimized, because fibers become resistant to degradation. So all the process is an equilibrium between degradation and aggregation. So you have two kinetics in the system. And also this can make reasonable why you can have type A or type B fibers. If you just reduce the concentration, you will have type B, because if you reduce the concentration, the amount of fragment is reduced. You don't reach the critical concentration. The fragment is extremely unfolded. We have simulation showing that the fragment lose a lot of strength, the helix,
which would make it more accessible.
More accessible to proteases. So you can have two kinetics going on. One is the aggregation. That when you have the aggregate, you have seeds and you accelerate and you rescue some of the monomer and fragments. So I think when you introduce a proteases in the system, it is not anymore a two-state transition from native to, but you have many pieces of in the system, and can be different from one tissue to the other, if you have a good nucleation, if you don't. So I think I perfectly agree with you. You can have a complete degradation without any fibers if you go at low concentration. In vivo, you have 3 micromolar TTR circulating, 2 micromolar concentration of TTR. So you should imagine that for many years you have a complete degradation of, so it takes 70 years, 75 years, 80 years for wild type TTR to get amyloid in the heart. So for many years we are protected. And it's possible that also you have some physiological function, the degradation of TTR, so the pathway, because TTR is so stable, you should boil to dissociate TTR actually.
my question is also related to the Pierre's question. So how much extent of the molecules to be partially digested? That means a small amount of the proteins digested, partially digested molecules can trigger the amyloid fiber formation to impact the TTR molecules, or all of the amylose.
The yield is not very high in this condition. We should find a proper equilibrium, but a lot of protein is not digested.
So that means a small amount of the partially digested TTR can induce, can propagate.
Of course, you have a seeding effect, yes. And both monomer and truncated go into the fibers at the end.
So under these conditions, kind of the seeding reaction happens through the partially digested TTR.
I don't think the tetramer go into fibers at all. So I think only the dissociated protomer go into
so the two dissociation, at least minimum level of the proteolysis is required.
Yes, yes. Proteolysis is required. When we sent to Carl Robinson, he's working on native mass spec, and he found completely different stability when you clean or when you or what here.
And finally, I'd like to confirm, so all the fibers contain intact molecules.
Yes.
But they are kind of dissociated.
Yes, monomers.
Because of the proteolysis of the rest of the.
You break up the tetramer. The tetramer dissociated. Right. I can
Last question, please.
I'm sorry.
My name is Suzuki, and thank you for a very nice talk. I'd like to ask what kind of seed did you use in your aggregation and evaluation study?
We use the seeds obtained by the first aggregation. So
TTR aggregation?
yes, in vitro. We can use both the ex vivo, but in this case we use the fibers made with the trypsin digestive or the plasmid digestive.
Thanks so much.
Okay, thank you very much, Professor Berotti. So let's move to the next presentation.